All right, so I will go back to the example from last week. So, we had the following. Simple linear regression model using empty cars. So we had this. So we were looking to see if weight of the car in some sense influences miles per gallon. So this is what we suspected was that obviously the more your car weighs, the less you travel per gallon. So you're right. So this means that you probably need more in your car. Basically, you probably need more gas, right, to travel. Like big cars tend to guzzle more, most likely. It's probably true. It's almost like, like when you're heavier, you tend to eat more to get more fuel. But yeah, so it's almost the same concept with a car. So anyways, you can see here that our first line of defense is to just look at the scatter plot itself. And I would say that whenever you're looking at bivariate statistics, before you even consider doing a GLM, so before we even do this part, which is the GLM part, we should just look at the scatter plot. So your first line of defense, whenever you're dealing with two continuous variables, is to do a scatter plot, right? And scan the question carefully when he asks you to make sure you know what X and Y is, because X is the variable that is less likely to suffer from measurement error. It is the independent variable, and the variable you think has measurement error or possible statistical noise is a response variable. Usually it's very transparent in the question, but make sure you're keeping in your mind which one is which. You don't confuse them in the assignment. So we look at the scatter plot and we have this. So, oh, I forgot to actually put the points. So that was just the grid. But so if we look at the scatter plot, we have the following. We just have the scatter plot of points. It shows this kind of downward relationship, right? It looks to me moderately, at the very least, linear relationship that is negative, as in like, the heavier your car is, the less miles it travels per gallon, basically, right? So you need your smaller cars tend to travel far further with less gas, basically, right? So now we want to put a linear regression. Now, the reason why I look at the scatter plot first before I even do any linear regression is because if I look at my plot and I notice any lines that don't, to me, appear to be, nicely linear, and if you see some kind of curved linear thing in the plot, I may not want to use linear regression. So because even if you have a very strong relationship in your plot between two variables, but it's not linear, you shouldn't use linear regression. This is why your first line of defense before you even put a linear regression model through it is to ensure you actually have a linear regression model, not some kind of curved linear thing that needs another kind of line of best fit, right? So we want to find the best fit. And if linear line is not the best fit, you wouldn't want to use it. But to me, it looks like linear regression is not a bad fit because I can see a downward linear trend. And so I'm going to put a line through it. And that's what I'm going to use this geo method. Now, I just want to point out that this doesn't give you the coefficients, right? It just puts a line of best fit. Oh, somebody's asking a question. Oh, can you people hear me? Can you guys hear me? Oh. Okay, so hopefully you can hear me. So sorry if you can't hear me, Irene. Oh, okay. So just to be clear, you want to make sure that your line of best fit's actually, the best fit is actually linear regression, right? So you can notice here, I don't actually have the estimates themselves. This just puts the line of best fit, which is the blue line, which is the theoretical line. And then you get the confidence intervals. Notice that when your points are sparse, your confidence bands are actually wider, right? So when you have more data, your confidence bands are actually narrower in the center, right? The other thing you want to note is that obviously this blue line represents the expected value on of X conditional on Y, basically, right? So it's a conditional expectation. And of course, when you have statistical noise, your points may not exactly sit on the blue line. Like this one is far from the blue line. So you're going to have for instance, here, this is an underestimation because the point here is far from the line, whereas here is an overestimation for these points. But in general, the confidence band is narrower when you have more data. Okay, but to actually fit the model, you need to use the LM function, right? So we're going to, no worries, Noreen. So to fill the LM model, we're going to use this model summary here. Now, I did fit that. And so here's my summary. So you can see here that I get this information. There's a couple of things you actually have here. So we almost never look at this part here, but I find it kind of fascinating because you can actually see the shape of your residual. Like the residuals themselves are informative insofar that it tells you whether or not your actual response variable is distributed normally, because if your residuals don't actually have a normal distribution to it, when you look at the plot, right, you would actually notice that you perhaps don't have something that looks normal. So from looking at this, you can see the minimum, the maximum, the median, Q1 and Q3. And I guess it's kind of hard to assess just from this alone whether or not you actually have data that's distributed normally. One thing you could do, of course, is to scan the distance between Q1 and the median and Q3 and the median. So if for instance, your Q3 is closer to your median than Q1, you would have like potentially less skewed data. Whereas if your median is closer to Q1 than Q3, you might have right skewed data. So you can look at those things, look at the little distance and see if the median is equidistant. And the other thing you want to check is if you have outliers. If you have very heavy outliers, you may not have a normal distribution either. So, but then this is not enough. You might want to look at the actual histogram, and there's other plots we'll look at in this tutorial to see what we have basically. But the actual estimates are here. This is the estimate for the intercept. And notice that you can't actually interpret the intercept unless 0 is a possible range in your data, right? So if 0 is not a data point, you may not be able to interpret the intercept, which is supposed to correspond to the average value. So the intercept is supposed to correspond to the average value you get in your in the mean response you have. So this would be in the context of this question here would be the mean miles per gallon of the I guess I wonder if these are US cars. Yeah, so the mean miles per gallon for let's say US cars, right, when the weight of your car is 0. So what the thing is, the weight of your car cannot really be 0, right? So that's why this intercept doesn't have a real interpretation, because it should be the average value, which is the intercept of the average miles per gallon your car tends to drink. But this can't really make any sense when you don't have a weight of 0 in your car. So you think to yourself, is your beta not interpretable? It may not be interpretable if it doesn't make sense within the range of possible values for your independent variable, right? So think about this in that way when you look at your assignments, right? But for the most part, we're interested anyways in the slope, right? So we're really interested in conceptualizing whether or not there's an association between the weight of the car and how many miles you get per gallon that your car drinks, basically, right? So to assess significance, we look at this part here, the p-value and also t-value. Now, I want to point out that without having the there's 2 ways to go about it. Last time I said that you could look at the t quantile, right? So you can use qt here, which is qt corresponds to the quantile for the t distribution. So you have to specify a data frame, which is going to be, degrees of freedom, which in this instance here would be 30 because you have 32 data points, as you can see here, right? So n minus 2, so you lose 2 degrees of freedom. So I'm going to write this down here. So notice. So as an aside note, 2 degrees of freedom, 2 degrees lost to estimate the intercept terms, slope term. So really, degrees of freedom is, the following, n minus 2. So this is why you actually see in the output here that degrees of freedom is 30. So if you want to compare your t statistic, which is this, to the t critical value, so therefore, you can obviously say you're looking for the following: the probability of the absolute value of t right? That's what you're really looking at. And the absolute value of t in this instance here is obviously 9.59. So you want to look at this basically, right? It's going to be equal to, in this context here, so you're looking at this basically, right? So it's going to be equal to the p-value you see here. So it's in this into 1.29 e to the minus 10. That's what you see, right? This is equivalent to assessing whether, you know, your t value, the absolute value of t, is actually bigger than the t critical value. And you might say, what is that? It's going to be equal to t at your appropriate degrees of freedom, basically. So it's going to be at, you know, in the example here, 0.975, because I'm going to use the alpha of 0.05. And the degrees of freedom is going to be equal to 30 in this instance here, right? So, so I'm going to put this into this. So that's going to be 0.975, right? And then you have 30. So when you look at this, you're looking to see if your t value is bigger than the following, right? Because that means it's going to be in the tails. So you can see that obviously our absolute value of t is certainly bigger than that, which is why the p-value is very small, because it means your actual test statistic is in the tails. What is it actually saying? It's saying the probability of seeing a test statistic, so the probability of seeing your actual estimate for beta naught, right, being that far from zero under the null assumption, which is the following down here, right? So the null assumption is the following here. This beta 1 is equal to 0 is unlikely, right? So you shouldn't have seen a beta 1 value that extreme if the null assumption of 0 is true. So in this context here, we will reject the null hypothesis and conclude the alternative, which is that beta 1 is not 0. So I'll knit this so you guys can see what it looks like, right? So we're always trying to assess, at least in the simple linear regression setting, right, whether or not we actually have an effect with beta 1, because there's really only one coefficient we're looking at. But you can imagine in practice, we're almost never looking at the simple linear regression setting because we have no reason to believe that only one covariate in general is going to impact significance. So what we're looking at is the following here, right? So you can see that it looks like this, right? So you can see that this is the test we're looking at here. But so the question is, if this is really true, should you have seen a t statistic this extreme of, you know, 9.559? You should not have, because what it's saying is your beta coefficient is too far from 0, right? Now, this is informative. How come? Because now I can make a conclusion. So conclusion I actually made here is that since our p-value is less than 0.05, we will reject the null hypothesis and include the alternative. Now, this is not enough. If you just put this part here, you didn't do enough to get full marks. You need to specify within the context of your study, right? So the study is actually looking at weight and miles per hour driven, right? So it appears that the more a car weighs, the slower the car moves per given mile. Like it really takes more to end up with a situation where your cars, it takes more if your gas requires more. Sorry, you require more what? More gas to move the same amount of miles as a smaller car does. So that's kind of not great, obviously, right? But that's how it goes. Yeah. Okay, so that means you want to not only make a conclusion within the context of your study. So since the p-value is less than this, reject the null, but then you want to answer the question in the context of your study to ensure that you are being very explicit, right? So make sure you're being very explicit. Okay, now the issue is that even if you actually find an effect, you don't know if you truly found an effect. Why is that? Because you just don't know if you even use the right model, basically. Remember, this model works, this link function of like y is equal to mx plus b only really works if you truly actually have data that is disputed normally, right? But if this is not true, then this model may not be permissible, even if you look at, even if you look at the scatter plot, and it looks like the following. Even if you have a scatter plot where it looks like this, where it looks nicely linear, right? You still don't have, it still may not be the case that your actual response variable is linear, right? So then it wouldn't be enough to just make a conclusion. We need to check the residual plots, right? So I did say that there are a couple of plots you could check to assess the residuals. The first thing you might want to check, so actually there's really technically speaking, I kind of looked at 2 plots in particular, but you could use plot and put your model in, and it will give you 4 plots. I just only really wanted the first 2, so I put this extra line of code, but if you just run this code here, you get 4 plots. So we can see that the first plot is really the residual plot, right? So now you're comparing your fitted values, which is a function of your, so notice that your fitted value is a function of your predictor variables, right? So this means that even though R's default is to put the fitted values against the residuals, you can also put your fitted values against your predictor variables to look at the residual plots. But in the simple linear regression situation, it shouldn't be too different. But the reason why they'll put the fitted values against the residuals in the context of, like, for instance, multiple linear regression is because your fitted values in multiple linear regression will be a function of multiple predictor variables, right? More than just one. And so you wouldn't want to compare your single predictor variables against the residuals, because you may get patterns in the plot just because you didn't account for all predictor variables. So when you have multiple linear regression, you may want to use the fitted values against the residuals. But in the simple linear regression situation, you could have also used the predictor variable itself against residuals. But because you want to make sure you're accounting for all the predictor variables in the MLR situation, you may want to use the fitted values. This is why R uses default the fitted values against the residuals instead of using the predictor variables themselves, because if you have more than one predictor variable, of course, you have to think about this, right? So that's why we have that. Okay, so you can see here that you want your plot to hover around 0. You might say, why? The reason for this is that the residual is the difference between your observed value and what you fitted, right? So for a given value of X, what did you actually see for your YI, and what did you actually fit? Now, in theory, you want this difference to be close to 0, because of course you want to say that your model did a good job at tracking your YI, basically. But there's an extent to which it fails to capture it, basically, right? This is why the expected value is 0. Like, on average, if your model is actually making sense, you expect the difference between YI and Y hat is 0. So this is why the line theoretically sits along this space here, right? But like I said, the extent to which your model fails to track completely your YI would be the extent to which first of all, your points are not sitting on that line, but also the extent to which your points deviate too far from said line, right? This one doesn't look too bad. I mean, it's not great. You can see there's some kind of upward shape. So probably we need to think about this, like Y, for instance, is the points appearing to be larger. Y is the residuals appearing to be larger at the beginning and end, right? And you have some outliers, which they kind of label. So there's an outlier Toyota Corolla, Chrysler Imperial, and there's something Imperial, and there's something else I can't read up here at 0.128. It says flat or something, but yeah. There's 3 different outliers here, and then it looks like there's an up shape, so we may need to do some investigation. So this tells us kind of like if you have non-constant variance, right? This is the residual plot assesses non-constant variance. So to assess non-constant variance, right? So it appears we have 3 outliers, and we have some upward U shape. So this may indicate some strange non-constant variance somewhere, and where you have this weird shrinking effect in the middle, but then it gets bigger at the end. And basically, but let's see what the QQ plot shows us. We get this thing here, and you can see the same 3 outliers kind of cluster up here, right? Which kind of gives us, it looks a bit like the distribution is kind of not too bad over here, but because of the outliers, it almost makes it appear like it's right skewed or something, like this upward cup makes the distribution look somewhat non-symmetric, right? So we may have to think about this, like maybe treatment of the outliers. But the only issue is that, does anyone see the problem with treating the outliers here? what's the problem with like just removing the outliers? So usually when you have big outliers and you have a large data set, if the outliers are influential, you're going to maybe to remove them. Does anyone see what the possible problem we may have is with just removing the data points in this particular data set? Like what could be an issue we could run into here? Does anyone know what the possible problem is? So the issue is that we have a really small data set, right? And because we have a small data set, if you remove too many points, you may get an unstable model. Like you don't want a model that truly honestly just tracks your data, but doesn't really track the model, in the general sense. You don't want to pick up patterns in your data, right? You want to actually truly pick up patterns that are specific to the population at large and not patterns that are kind of relevant to your data or artifacts. That's not what you want to pick up, right? So when you remove too many data points, that's the issue basically, right? So we have to be mindful of this for sure, right? To avoid situations where we end up with almost a contrived model that only really doesn't really reflect reality, right? So this is why we are a bit careful, reticent to kind of just, blindly remove stuff, right? So that's something we definitely think about for sure. Yeah, so that's definitely a different issue that it's always very salient in our minds for us. Yeah. Okay. So the other thing we have here, I'm not going to talk about too much because that's why we don't need to know this too much just yet, because I don't think, especially this, I don't think Ken talks about dealing with leverage points just yet. So I wouldn't worry about the fourth plot. And even this kind of is a rescaling. So this is a rescaling of the residuals. You may want to think about using this. So this is actually similar, saying something similar to the first plot here, except it scales that. So I don't know if we've talked about standardized residuals, right? The reason for you to potentially standardize residuals is because sometimes they don't have the same standard error across each residuals. You can even see it here, right? You can see that because there is some kind of variation in the larger and smaller values. Sometimes you use standardized residuals when you suspect the standard errors on each of the residuals are not the same. So you have to standardize them and you get a more appropriate assessment of the actual fit, because you can see here that when you standardize the residuals, even though the line looks somewhat constant, it's far from zero. So there's a funny thing, and the line is constant, but it's not at zero. So you may think about like our residual plot and our residuals in this framework basis. So this is why but I would really say these two plots here are the ones you care about the most, which is why I actually pulled this code here basically. So when you actually run it, you get the first two plots you're kind of really interested in, which is just these two, right? So this is why I've done this basically. Any questions about this so far? Does anyone have anything they want me to go back and cover again in simple linear regression before I move on to multiple linear regression? So most of your assignment is actually on. The other thing I will say before I move on to multiple linear regression is that you could look at the following. I wonder if so if you want to pull up the fitted value, so like let's say you want to pull up, let's pull up residuals to make an histogram. I just want to see if I just want to show you guys that you could also visually look at the histogram too. So I think that you could do something like model residuals. I want to see if this kind of, yeah, so there they are, right? But I want to, yeah, so these are the residuals for your model, by the way. You can see them, there's only 32 data points, and you can see that the residuals are for each of these cars. So, here's the phi 8. So this is the actual other residuals. It's a phi 8 actually. So you can see that this is the outlier, the other outliers over here. So there's an outlier at phi 8, Chrysler Imperial, and there's, I think it was Toyota Corolla. So these are the outliers here. This one, and this one here. So if you're ever curious to figure out where the outliers happens to be, you can use this. But I wouldn't, but if you want to actually apply your residuals, you may want to do something a bit different. So this is if you want to, check your outliers positions, you can use the following code. but obviously remove the hashtag. I did that because I don't want it to run, especially if you have a very big data set. You wouldn't want to run this like this. But if you want to actually fit your residuals, you can do the following. I think there's a function built in R that's something like, so I'm going to call it res. I think it's in the, residuals. Yeah, I think it's like resid of like your model. So let me see if it runs. Yeah, so you can see that this is it. So if I look at your head of residuals, so you can see that they're all here. Right, so, oh, I don't want this. There you go. So they're all there. Hey, that's kind of weird. Let me see if it actually works. Oh yeah, it does. So it turns out that I could have actually also used this. It's kind of funny. So anyways, it turns out I could have just actually, these are doing the same thing. I kind of relabeled my visuals like this. It turns out I could have also just done this. So it turns out that I probably could have just, let me just confirm this. This is so funny. Let's call it res2. Like I used R for so many years, but now I'm just learning like, there are like 1,000 ways to do the same thing, right? So if I look at hist of residual 2. Hey, okay, yeah. So these are two ways to do the same thing. I honestly thought that this was just a display, but it turns out it actually pulls your residuals too. So anyways, there's more than one solution to a problem is a moral of the story, right? So you can see this is your residuals. Does anyone see what the issue with these residuals are? Like, what do you notice about them? What do you see? Does anyone see the issue with the residuals here? Yeah, it's a bit right skewed basically. So this is the problem, right? So our residuals look a bit funky, right? So, this is what we're looking at, and it looks a bit, it doesn't look quite symmetric, or right? So this is, you see most of the values are clustering here. Then we have this skew all the way to 6 and 8. And this is actually captured, by the way, as well in our QQ plot. If you have a look, you can see that it looks a bit like this, right? So this is when you have this upward cusp, it looks like this. You kind of have a bit of a skew, right? Now we definitely have 3 outliers, which could be why you could be pushing this up like this, but this is definitely an issue we need to think about, right? Because you're making a claim that the assumptions are satisfied. Your distribution is normal, your residuals are showing constant variance. And if you have some kind of evidence it's not true, you may ask yourself if this is probably the best thing to do, right? I want to give you a code though to make it look nicer. This plot is not great. I wouldn't use hist. I mean, that's base R, but he did tell you to use tidyverse. So I'm going to translate things, right? So I'm going to do the following. I'm going to make it so you can actually, table of, I'm going to call it residuals. I'm going to redo it so you can actually, yeah, I'm going to redo this so you can actually use it in ggplot, because of course there would be some mark deductions if you use base R. He did tell you to use tidyverse. I'm going to read it. I'm not going to encourage you guys to use histogram, right? That was me being a bit lazy. But you guys know that if you want to actually use ggplot, you have to feed it a data frame, which is why I called it tibble, a residual, basically, right? So I'm going to then make a ggplot for this, a ggplot of like residual, so x is equal to res, and I'm going to do plus geom hist, and I want to make it look nice. So let's say, color equals, color equals, I think it's actually this. Let me just make sure this actually works. Oh, it's histogram. There you go. So this is this. And now I want to do something else because this is horribly ugly. So fill equals rad. And let's also, we may have to change the bins because this is not good, right? So let's call it, let's say bins equals, let's say 6, because it does look kind of sloppy, right? So now if I run this, I get this, right? So this kind of reveals the shape of it more, right? Which shows it's skewed. Right, and maybe, so you might want to change the bins yourself to make it, at best, you may want to use maybe even 7 potentially, let me see, but definitely don't want to go above 7 because you might lose a shape, so I wouldn't go above 7. because the data set is small, right? So when your data set is small, if you use too many bins, you lose the shape. Okay, so this might be a bit nicer, of course, than using histogram because that's base R, but you don't get very nice things in your plot. So this isn't probably a nicer plot. You could, of course, change, right, the label, right? So you can make it as pretty as possible and say something like, you know, residuals, or you can say here, fitted values. No, is that fitted values? This is the residuals, actually. It's not, it's the residuals. Right, so it's here in the residuals. Yeah. So it's like this. Yeah, there you go. So this is your residual plot, which then you know that there's a bit of an issue. You may want to perform a transformation, which he hasn't talked about just yet, so he probably won't ask you, what would you do to fix this? He probably would just say, does your residual plot show your assumption was met? You may say yes or no. For your final project, he probably will tell you to do some kind of transformation. Maybe it's log or square root, whatever, that allows you to kind of shift your plot so that the response variable looks more symmetric. So then when you actually perform the actual linear regression, instead of having something like, you know, instead of having MPG as a function of weight, you may have, like, let's say log of MPG as a function of weight, so that, you know, you adjust for the fact that you have a skew of some sort, right? Okay. So now let's turn our, you know, ourselves over a bit to MLR, because this is a more realistic setting, right? So in practice and actuality, most of the time you're going to be dealing with more than one covariate. So we need to think about this basically. Okay. So I'm going to add another variable, and I deliberately added one that is actually discrete, just because I wanted to point out that even though in general, when you have a linear regression, your first instinct is to plot two bivariate variables. So you want to plot x against y. Sometimes your x is not actually even, you know, something that is, you know, continuous, in which case it doesn't really make sense to do a scatter plot directly, because you're not going to get something that makes any sense, right? So if I plot, for instance, x against y in this framework, all I'm going to get is just a bunch of, like, so if I literally took a factor of cylinder and I plotted against weight, what I would see is actually three different bins probably, and we can actually have a look and see it just out of curiosity to show you what it does. It looks kind of funny, but let's see. X equals, let's say, x equals x equals, I'm being lazy at this point. Okay, as that factor of cylinder, let's see, it works. And then y equals, I want to look at MPG. Let's see if it first works. Yeah, so we get this thing here, and you can see that it immediately is going to give me a scatter plot where I'm looking at all the points of 4, 6, and 8. So instead of having a nice linear trend, it's going to put a distribution of points across 4, 6, and 8. And you may see some kind of upward trend or a downward trend, probably, where you see it going down as a function of the weight of the cylinders, because of course 4 cylinders is going to weigh less than 8. So you might see a downward trend like this, but it's not going to look nicely linear because this is discrete basically, right? So if I have a look here and I just add, for instance, GROM points, and I put something, yeah, so if I just do this, let's see what we get. And I can show you why we wouldn't add a line of best fit, because it doesn't make any sense. You can see you get this basically. So like I said, you get a downward trend that does like this. So the weight is going down as the cylinders increases. Why is that? Because a car that has 8 cylinders weighs more than a car that has 4 cylinders. So of course the miles you drive per gallon is going to be more for a car with only 4 cylinders, so it weighs less than one that has 8. but you don't get a nice linear trend because each class is a separate thing. So you just get a separate pattern that does show some kind of clear relationship, and you can actually do a fill basically, right? So you could probably add like a fill, so you can color coordinate. So you have like, you know, green, red, and blue, green, red, or blue, whatever. But you can see the point is made here, right? So you cannot do a linear line. So I wouldn't put, for instance, plus geom point, or I wouldn't put plus geom smooth line equals LM because it doesn't make sense. But recognizing that the weight does go down, recognizing MPG does go down for each weight, I will put it into the model as a factor because I can see that from the plot, even though I should not put a linear line of best fit, it does give me some information to know that there's some kind of relationship where the more the car weighs, the more miles, the less miles it goes per gallon, right? So I can still put it in as a factor basically, right? So which is what I'm going to do. And so model 2 now has a second covariate. And now because it has another covariate, this makes this multiple linear regression model, right? So let's run this. And then if I look at the summary of this model 2, what do I get? I get this weird thing. You can see that, first of all, you get the initial, you get an intercept covariate, but it's going to change now because it's going to reweight itself because now you have another covariate you added to the model. It's not going to be the same estimate as what you saw up here. So it's gone down. Oh, someone has a question. You don't have to use a box plot because your response variable y is still actually, that's a great point actually, Ken. That's actually so good. So I probably could have used, that's actually super smart. I think you're probably right. So instead of using this graph, which I don't think I did the optimal graph, I was looking at what Ken said. I actually think that his idea makes more sense. And you've done it in class so many times. When you have two different, so what he's saying is that how come you did this linear line here, which he's actually probably correct, right? Why did you do this line here? Right, so you see, I did as dot factor, but I probably could have done box plot basically. So you see, instead of doing this, probably I should have done a box plot. So it's just a geom box instead, box plot basically, right? So I should have done geom box plot, right? So instead of putting geom point, I should put geom box plot. Then I would have gotten a box plot for each different group basically, right? So that's what he's saying. So let's see if we can actually do that. Right, so let's see what we get. So you get this. So his idea makes a lot of sense. It probably, I don't even know why I didn't think about it. Instead of using a linear regression line, it's probably better to use a box plot because you have 3 different groups and each group has its own weight class, but there's some outliers ironically in these 2 groups in this last class here, but I digress. You could probably use geom box plots. I think he's making a lot of sense. So if you want, it's probably smarter to use. So they'll always say that you got the same pattern from the points, but yeah, absolutely correct. I think a box plot makes more sense in this framework here. Box Cox you could use, by the way, if you're referring to the transformation, you could use a box Cox, although it's not something we talked about just yet. If you want to transform your MPG, it's actually shifted, it looks normal. So if you look at the information we have here, we know that the residuals in the simple linear regression framework looks skewed, and then you might want to do box Cox to transform it to something that looks normal. That's probably a different part of the course. So no, I don't think he's talked about that just yet. I don't even know if we'll talk about it at all in this course, though, because it's probably a bit much to talk about, but we'll see. But you could use it in your final project. If you guys have a final project and you want to use a transformation because maybe your data doesn't look symmetric in the response variable, but you want to perform a transformation, box Cox could be something you might look into for sure. Okay, so if you look at the summary, you can see here that you get a couple of things. You get the intercept is different. You also get the weight is going to change. So notice that the weight variable is not the same as what it was before, right? So notice that it was like -5.3, but now it's actually smaller. The estimate shrunk because now you get some of the weight, some of the information is going to the cylinder classes. Now notice that you get only 2 levels here, even though there are actually 3. That's because one group, which is the 4th group, so which is the weight class 4, is the reference group. So the intercept term here is going to correspond to the weight class 4. So when you interpret this model with these two, you're going to say, given that the person's in group 6, you got a decrease in your miles per gallon relative to group 4 by a factor of -4.2. You get a decrease by a factor of 4.2. If relative to, or for instance, if you're in weight class 6, you say, well, relative to 4 cylinders, if you have 8 cylinders, you see a decrease in the miles you drive per gallon by a factor of 6.07 miles per gallon, right? So you can see that these two estimates are going to be in comparison to the reference group, which is 4. This is why you only see these two estimates here. So you're going to make the comparison in regards to reference group 4. So it makes sense as to why it's negative, because of course the miles per gallon goes down when you weigh more. So you're going to say relative to group 4, you see a decrease of 4.2, miles per gallon if you're in group 6, and the same thing for group A. You also have the estimates for this, but now you have to actually keep in your mind that you need to interpret this in the context of the fact that you have multiple predictive variables. So how do I actually interpret coefficients? I need to be something like, holding the, so if I wanted to interpret, for instance, if I wanted to, for instance, interpret the weight coefficient, I would say holding the cylinder class is fixed. That means that I'm looking within the same level of a cylinder class. So if I hold the cylinder class fixed, it means that every comparison I'm making for the cars is going to be among the same class. I'm going to look at the weight of cars for those who are in cylinder class 4, or I look at the weight of cars for those who are in cylinder class 6 or 8, and I'm not looking across different groups because I need to hold it fixed and then look at the variation in weights within each group, basically. Otherwise, you cannot know what the influence is of weight alone if you look across the groups. You have to look only within each group and see how the weight changes the miles per gallon, right? Because the distribution of weights within each class. So if I hold the cylinder class fixed, right, then the change in weight, right, the change in the miles per gallon driven as the weight increases 1 unit is 3.20, let's say, right? So that means that I'm saying that the actual change you see in the, when you increase the weight by 1,000 kilometers, right? I guess by 1,000, I think it's by 100 pounds, 1,000 pounds, right? So if you increase the weight by 1,000 pounds, that's 1 unit in this instance here. It increases the miles per gallon by 3.2. So we should be a bit careful here. Let me see. Yeah, the weight increases. Yeah, there you go. Because 1 unit is actually 1,000 pounds, right? Is this? Yeah. So I have to put this first here, holding the cylinder class fixed. Otherwise, I don't know what the influence of weight is alone if I don't hold the cylinder class fixed, right? So intuitively, it makes sense because you can see even within each class, as your weight increases, of course, you're going to increase, right? You're going to decrease your miles per gallon. Okay, so this is how you would interpret it. And you could do the same thing. You would say, or you could interpret, you could say holding the weight fixed. If I look at the cylinder class increases, or the miles per gallon decreases for a cylinder class of 6 by a factor of whatever, basically. So you need to say holding the other covariate fixed is the general thing, basically, right? Because you need to ensure that the influence you're looking at on your response variable is only attributed to that one covariate. You're not having a conflation of factors, basically. So then the question you're asking is that how do you determine significance in the framework where you're actually looking at more than one covariate, right? So we need to change the scope of the question a little bit with a twist, right? So instead of saying, well, beta 1 is 0, you say all the beta naughts are 0, all the beta i's are 0, because truly, if you have no effect, none of these covariates should be significant. And in that framework, you're looking at the model where you only have the intercept term itself, basically, right? So in a situation where you truly actually have, right, no intercept term, basically, right? Sorry, in a situation where you truly have no significant predictor variables, you only have the intercept term, and you're really saying all the beta i's are 0, basically. Otherwise, for your model to be significant, you don't need all of the covariates to be significant. You just need one of them to be, basically. So the question is now, you're not asking for them all to be significant. You're only asking for one to be significant. So you only ask at least one of them is significant, because you've now changed, right, the scope of your question. So you're not asking, again, you're not asking for all of them to be significant. Sorry, you're only asking for some of them to be significant, right? So this is the way it changes, basically. And this is important, obviously, because when you want to reduce your model in your final projects, you may realize that the full model, which you call saturated, may not be the final model you work with. You may look at the models that has only significant predictive variables in your model, right? You don't want to look at every single one. So this is why this becomes kind of important, right? So that's how that's going to work. And you could, of course, and the last thing I just want to point out is that you could also look at the plot, you know, like you could look at the, let's assess the residual plots. You could look at that again in the context of MLR. Now you have something like, you know, plot of, let's say, model 2, and now you have, let's say 1 to 2, right? So you have this, basically. So you look at the residual plot here, it looks actually better than the previous one. It's a bit better. So it looks like we were missing some information when we omitted the similar class, and you can see that, you know, the plot is slightly less ridiculous. You still have an outlier here. You still have that same outliers, but the plot looks a little less very temperamental, right? So it appears that we probably had non-constant variance because we were missing some information, right? So, you know, it seems like, you know, we perhaps had non-constant variance because we were missing information from our simple linear regression model. Sometimes when you have really erratic residuals, it tells you that you're missing some your covariates, that you're missing some information from your model, that your covariates are kind of, you're missing covariates, basically. So that's kind of another thing you get from the residual plot. But that's it for today. I will post this lecture and the code for you guys to practice for your reports this week, because it is based on multiple regression and simple regression, like the residual plots, and as well as dealing with simple, like interpreting coefficients in multiple regression, etc. So good luck with that tonight, or today when it comes, or I guess tomorrow when it comes out, not today. Have a good afternoon, guys. Bye.